Hello, this is Ahmad Mirabi. In this video, I'm going to solve a thermodynamics problem about thermodynamics cycle and heat engine, efficiency, heat capacity of gases. Many items and topics are involved in this problem solving. Let's solve one example. Figure shows a reversible cycle through which 1 mole of monoatomic ideal gas is taken. So, a reversible cycle through which 1 mole of monoatomic gas. So, it's a monoatomic gas like neon or argon or krypton, whatever. It's an ideal gas, so we can use the ideal gas laws. P0 and V0 is the coordinate of this point. V and P are given to be coordinate of this point. P equal to P0, V equal to V0, and P0 is 10 to the 5 Pascal, and V0 is 20 liter. So, converting 20 liter into cubic meter, it will be 200th of cubic meter. Okay? Calculate the work done during the cycle. The work done during the cycle is the area inside the cycle. So the area inside the cycle is V0 times P0, length times width. So V0 times P0, which will be 200 times 10 to the 5, which will be 2000 joule. Is it positive or negative? Let's pay attention to the top process. The top process is the volume is increasing, so it is expanding. Because it is expansion, the work is negative. So the top, let me write here, the top process expands, and therefore the work of that is negative, and because that work dominates all other works, the work of the whole cycle is negative, and therefore the work is calculated to be negative 2000 joule. So 2000 joule of energy is being delivered. Of course, because this is a clockwise cycle, you can learn by heart that clockwise gives the work and counterclockwise gets the work, but I don't recommend this. Part A says the work done during the cycle. Part B says the energy added as heat during the stroke ABC. So we learned that AB is where heat is gained by the system, and BC is where heat is gained. But in CD and DA, the heat is lost, because I said in PV diagrams, the isothermal curves are like this. So as we go top and to the right, the temperature are increasing. So this is TC and this is TA, and we can write TC is greater than TB is greater than TA. TB is in the middle. So the Q of the process AB can be written as, this is an isochoric process. In isochoric process, we just learned that QAB can be written as NCV delta T. N is 1, but let's keep it. CV can be replaced by 3 over 2 of R. R is universal gas constant. So now we have 3 over 2 of NR delta T. I can rewrite NR delta T as V delta P for this ideal gas, for this isochoric process, because I can write P AV equals nRTA, and once I can write the ideal gas formula for point B like this, nRTB, and therefore subtracting these, V times delta P is equal nR delta T. So instead of nR delta T, I wrote V delta P here. I know V and I know delta P, that's why I turned this into this, because I don't have temperature here. I wrote everything in terms of volume and pressure. So this is 3/2 times, what is the volume? The volume is 200. What is the change in pressure? 10 to the 5. So it will be 3000 joule. Now, what is the heat gained by the system in the BC process? It is NCP delta T. Why? Because it's an isobaric process. Pressure is constant. So now, because it is monoatomic, instead of Cp I can replace 5/2R, and because of the same reason, instead of nR delta T I can replace P delta V here. So because I don't have temperature, I turn it into pressure and volume. 5/2 times the pressure is 2 times the pressure is 2 times P0, so 2 times 10 to the 5, and the volume changes 200, and therefore these two can be cancelled away. This is 10 to the 4 or 10,000 joule. So we can summarize these two steps to say that in these two steps the heat is added to the system. So QH will be 3000 plus 10,000, so it will be 13,000, and of course the sign is positive. And because heat is added to the system and work is being done, of course it's a heat engine. Once it is showing one cycle of a heat engine. Choice C says, or in part C of the question says the efficiency of the cycle. The efficiency of the cycle is work over QH. What is the amount of work given here? 2000 joule. What is the heat given to the system? 13,000. So it is 2/13. It is 2/13. So let me do the calculation. We'll multiply it by 100. 2/13 will be 0.15 multiplied by 100 will be roughly 15.4%. So it is roughly 15.4% the efficiency of this machine. The efficiency of this heat engine is in fact 15.4%. Part D, what is the efficiency of a Carnot engine operating between the highest and lowest temperature that occurs in this cycle? The highest temperature is Tc and the lowest temperature is Ta. So Carnot efficiency is Th minus Tc over Th, or we can write 1 minus Tc over Th. In Tc, because ideal gas law is applying, I can write Pc Vc over RT over Nr. The number of moles are all the same, so dividing the two temperatures, I can neglect the Nr in the denominator and to write, I want to write everything in terms of pressure and volume. That's why I rewrote it as this. I think I need to reverse this because cold is A, hot is C. So it must be PA VA over PC VC. So the pressure of point C is double the pressure at point A, and the volume is again double, so it is 1/4. So 1 minus 1/4 will be 3/4, or 75%. This is the Carnot efficiency, which is the maximum attainable efficiency in a heat engine, in this heat engine. So part D says, what is the efficiency of a Carnot engine operating between the highest and lowest temperature that occurs in the cycle? Is this greater than or less than the efficiency calculated? Of course it is greater than the efficiency calculated in part C, because the real efficiency is 15.4%. The upper limit efficiency, which is given by the Carnot efficiency, is 75%. And this, everything matches here. Everything's good.